Welcome to Legends of Data and AI. Each episode includes inspiring and actionable data and artificial intelligence insights from global leaders across industries. Your host, Dr. Usama Fayyad, was the first Chief Data Officer at Yahoo and is Chairman of Open Insights and Executive Director of the Institute for Experiential AI at Northeastern University.
Welcome, everyone, to another episode of Legends of Data and AI, where we discuss topics, myths, and complicated realities of making AI and data work in companies, in organizations. I'm Usama Fayyad, Executive Director of the Institute for Experiential AI at Northeastern University and also Chairman of Open Insights. With me today is a very special guest. He is donning his data miner's hat today in honor of this podcast. We very much appreciate that for viewers who get to see the video. But Gregory Piatetsky-Shapiro has been a friend and a colleague for now many years, over 30 years. And he was there at the beginnings of the field of knowledge discovery in databases, which grew into data mining and data science and so forth. And for many years, he founded and ran KDnuggets, the biggest list targeting this community with news items, with items of interest, and so forth. Welcome, Gregory. It's an honor to have you here.
Thank you, Osama. It's an honor and privilege to be with you again. We've started many important things together, like KDD conferences, I think Data Mining and Knowledge Discovery Journal, and other things. So I'll be happy to discuss and talk to you listeners about what we have learned over the last 30 years.
Wonderful. So let me start with your long experience. You've been thinking about data, AI, and knowledge discovery in databases back in the late 1980s, 2 decades back into the previous century. Do you think we have come far since then? We certainly seem to have a lot more data, but as I always say, the advances in algorithms have not been as dramatic as the growth in data.
Yeah, I think there were many advances in algorithms, but maybe advances in algorithms are not as important for machine learning progress. Maybe we just need a lot more data and a lot more compute. But let me explain. I think there was a lot of progress since 1980s. Researchers then were working in databases that were measured in megabytes, like thousands of records. And business databases were only gigabytes, millions of records. Now we have researchers at, Google, Baidu, OpenAI, Meta, Microsoft, and other internet giants that routinely deal with many terabytes or even petabytes of data. Terabyte is 1 million megabytes, and I don't even want to think about what is a petabyte. So databases have grown by at least a factor of 1 million, especially since they now contain not only structured data, but also text, images, and social interactions and more. And for neural networks, it was known, back in the 60s that one-level neural network, a perceptron, was limited in its power. It could not learn, for example, an exclusive OR functions. Multi-level neural nets in principle could learn anything, but in practice, the training took too long. The results were not good. But thanks to perseverance of Jeff Hinton, Jan LeCun, Yoshua Bengio, and a few others, and huge advances in computational power in combination with much larger data sets, there was a deep learning breakthrough, starting with AlexNet winning ImageNet competition in 2012, and by a very large margin. And it turned out that big compute and big data enabled successful application of deep learning neural network methods that were essentially similar to methods that did not work in 1980s when they had small data and small compute. But besides bigger data and compute, there were many algorithmic advances, including, for example, transformers, generative adversarial networks, things like GPT-3 and other large language models, Reinforcement learning in combination with deep learning has achieved tremendous successes, from achieving superhuman levels in games like Go and chess to protein folding that was essentially solved recently last year. And there were advances in non-neural network methods such as support vector machine. XGBoost was invented relatively recently. And at some point, a very large percent of Kaggle competition winners were using XGBoost. And there were some other interesting phenomena like double descent, which I can explain later.
Yeah, no, thank you. That's a good answer. You have experience doing machine learning in many settings, in large enterprises, startup setting, and research and academia. In your opinion, is most of machine learning basically same set of algorithms applied across domains, or are there major differences as you move from one domain to another?
Yeah, the short answer is they're not the same. But here is my long answer. So I worked on applications in many areas, but mainly in consumer analytics like banking, insurance, telco, healthcare, analyzing healthcare costs, bioinformatics, microarray and mass spectrometry data analysis, and software. And first, in my experience, there was a big difference between approaches in research and applications. Academicians say that in theory, there is no difference between theory and practice, but in practice there is. In academic research settings, the goal is to get good publications for tenure, and this results in many papers that try to advance some narrow area without a particular concern to how widely applicable it is. When I was on KDD program committees, I have reviewed way too many papers that propose different variations of association rule mining algorithms with various refinements on the classical a priori methods that was proposed in 1994 by Agrawal and Srikant. But in my business experience, at least, I've never seen a useful application of association rule mining, despite the many papers I have reviewed. In business, the goal is to have business impact and ROI, and frequently simpler algorithms will be sufficient because they'll be easier to deploy and maintain. A famous example here is the Netflix prize from 2008. At that time, Netflix was mainly sending DVDs, which took a few days to arrive. So good recommendation of DVDs was very important. So Netflix asked users to rate movies from 1 to 5 stars, and explaining this to our users who may have forgotten that. And inspired partly by KDD Cup competitions, as Netflix people told me, they announced this $1 million prize for the best algorithm that will reduce the error in their method by 10%, which was then only about 0.1 star. So it took over a year. The winner achieved that goal by a very complex algorithm. $1 million check, very large check, was presented, but Netflix never implemented that algorithm because it was too complicated. And a few years later, it moved from 1 to 5 star rating to simply likes and don't likes. And once streaming has supplanted mailing DVDs, user rating became much less important. Netflix could simply use information of what users were actually watching to generate the recommendations. So in my experience as well, banks and telcos prefer simpler method that could be explained, such as regression or naive Bayes style methods. So when I was in research lab at GT, we considered clustering much less interesting or less sexy than a prediction method. But when I was working with some actual customers, with one bank, we had very successful application of clustering, which helped them significantly reorganize the approach to grouping their customers. And I've also done some very useful clustering studies for one very large software company. It was clustering how the commands were used, and both cases it was clustering helped to achieve significant business results. And also important to come up with a good story when explaining the clusters with good visualization that support this story. And to address the second part of your question, methods in different domains, they can differ a lot. For example, in microarray and mass spectrometer data analysis, there may be less than 100 samples, like people with a particular disease. Fortunately, there may not be 1 million people that have this particular disease, maybe only 100. But for each person, for each sample, actually, you may have tens of thousands of features. So here, it's very important to avoid overfitting. And so, we use various nested cross validation methods that may not be needed when you have, 1 million more times records than features. And even more important, bioinformatics is to focus on data errors, what is now very fashionable, and Andrew Ng is calling data-centric approaches. We've done data-centric approaches, then we just didn't know that it was called it. Like, someone says that I've been talking prose my whole life, I just didn't know it. And finally, data preparation methods need to rely on domain knowledge. So, one other example from bioinformatics, in one Alzheimer biomarker study, there were a lot of features whose value was 0, and that looked very strange to me. And upon investigation, I discovered that during preprocessing, the value that was less than certain threshold was automatically set to 0. So I was able to recover the original values, and that has improved results significantly. So to summarize, so business domain knowledge is frequently more important than the algorithm. And even more importantly, you need to have good business domain knowledge and work with domain experts to pose good questions. So my advice is question the domain expert assumptions, but never assume that you're more expert than them in the area.
Oh, great answers, and a very thorough treatment of kind of the differences across domains and the importance of domain knowledge. I love your example of Netflix. In fact, I don't know if you know this, but pre-pandemic, in 2016, Netflix actually claimed that, even though it's all now kind of recommendations online, they attribute about $1 billion of incremental value to the recommendation algorithm, just the ability to guess which is the next video you might like. So it had survivability, and it's good to know that they ended up going with a simpler algorithm and using a lot of the behavioral data. Related to what you said around kind of data-centric, how much of the action is really in the database management system versus the data mining algorithm or learning algorithm? Or is it mostly about the data content?
So there is this principle called data gravity, coined about 2010. Big data tends to remain where it is, and other things such as application machine learning method tend to fall to it. In fact, Usama, you were, I think, one of the pioneers of, or if not the pioneer of implementing machine learning algorithms in Microsoft SQL Server when you were at Microsoft in 1990s. So since then, much of the big data has moved to the cloud. So now Google, AWS, Microsoft, and other vendors have machine learning data science tools that work in the cloud with the data in the cloud. So I think in some sense the ML action for large data is now in the database in the cloud. So for internet scale and very large language models, they must have very specialized machine learning methods. So probably the content there is more important. So if I can rephrase your question, given a choice of having twice as fast database, twice as fast algorithm, or twice as much data, I would prefer twice as much data in almost every case.
A very nice guiding principle. I know you've shared some stories with us on how AI, ML, and data science was a key ingredient to success, or a major enabler in our ability to achieve certain tasks. Can you think of another one or two short but powerful examples of this?
Sure. Well, just in general, AI is maybe not from my experience, but from everyone's experience. So AI is already used many times a day by billions of people, probably by most people in the developed world. So speech recognition, when you pose a question to Siri, Google Assistant uses speech recognition, which is now done by deep learning based algorithms. So machine translation, we use Google Translate or other method, it also uses deep learning based methods. So I actually read and write in several languages, and I noticed a great improvement in quality of translation in the last 5 years. And social media interactions on Facebook, LinkedIn, TikTok, and other platforms are driven by machine learning algorithms. So when person uploads an image to Facebook, that image is being recognized to see what people are there, what content is there, but use that content to show to friends of that person, depending on the content, and so on. So,
Yes.
so machine learning is already widely used, whether people recognize it or not.
In fact, to your point, many people don't know that Google search engine it would not be possible without MLR, without kind of machine learning relevance to decide what is the most appropriate answer to a short query. It seems one of the phenomena I've seen is, and it always surprises me, there's little understanding of the deep dependence of machine learning on data. I mean, we all know that most of AI is really machine learning applied, and it sounds ironic that people don't understand that machine learning needs a lot of data. People assume somehow AI algorithms can reason about the task like humans do by drawing on prior or similar knowledge. How do you explain to the general public the very heavy dependence of algorithms on data, and not just any data? It's not the kind of data that humans consume. This is data that is at a much higher granularity and much more basic level.
So that's a great question. I've given it some thought, and I think I have an interesting example. So people do not understand how huge is their background knowledge of data is. So let's compare AI learning to children learning. So children can learn what is an elephant from a single example. So how do they do it? So babies spend their first few years, learning to walk, to speak, to do everything by watching the outside world by, for 12 hours a day. If the parents are lucky, they sleep the other 12 hours. So there are, 31 million seconds in a year, and if a baby can see 30 to 60 images per second, that comes to close to 1 billion images per year. And there is, of course, additional auditory and sensory information. So when children can learn what is an elephant from one example, it's because their visual cortex has already been pre-trained by watching billions of relevant images. But show to a child who doesn't know any Chinese, a complex Chinese hieroglyph, and he or she will not be able to learn it from one example. I've tried, and I couldn't learn it. Years of learning I required to master Chinese. And even better analogy, try to imagine that we have received a very long signal from outer space, from aliens, from Alpha Centauri, and we're trying to decode it, and it's very hard. So current AI systems are in a similar situation. For them, humans are like aliens from another planet. So another point here, I think public understanding of AI application usually goes through a phase shift from it cannot be done to, of course, computer can do it. When you and I were in graduate school, people used to argue, if you remember, computer will never beat a grandmaster in chess. There was a philosopher, I think his name was Hubert Dreyfus, who wrote a whole book arguing that computer will never defeat a grandmaster in chess. Then 10 or so years have passed. Deep Blue defeated then world champion Garry Kasparov in 1997. Some people still argued computer will never beat a Go grandmaster until, DeepMind program AlphaGo defeated Go world champion. So now people take it for granted that, computer can beat a human in almost every game, and probably go to the other extreme, expecting like too much from AI.
That's a very, very powerful observation and a good explanation of how much data is really needed. As you reflect back on the last 3 decades of work in KDD, data science, and AI and data, what in your opinion, what have we gotten wrong, What have we gotten right? And were there any big surprises other than the, chess players beating the best humans?
Yeah, I think that chess computers beating humans is not a surprise. I think the fundamental idea of learning from data was right. So it's probably more interesting to see what were the mistakes. What did the field get wrong? So in 1980s, there was this big interest in symbolic approaches in AI expert systems, and they've achieved some isolated successes. But after initial enthusiasm has passed, it turned out that this method didn't scale because they required very laborious human maintenance. On the other hand, neural networks seem to be impractical in 1990s, but when deep learning methods emerged around 2012, it was a big surprise that they were able to work so well in so many applications, and we still don't completely understand why they work so well. So there is, in biology, there is this idea expressed as, ontogeny recapitulates phylogeny. So there's some fancy terms, but what it means, development of an individual ontogeny approximately follows the same path as evolutionary development of its ancestors. That's phylogeny. So, for example, human embryo at some point has gill parts and tail following our, very early evolutionary ancestors who lived in the ocean. So what's the relevance or analogy to AI? So I think people can argue, and I probably agree with them, that development of artificial intelligence should follow the development of human intelligence. So start with neural networks that can do what a baby can do, image and sound recognition, and then layer on top of it symbolic reasoning. So maybe that's kind of one approach to do it. And then there were some other interesting surprises. So let me mention just one idea called the double descent phenomenon. So in classical machine learning, once model complexity passes a certain threshold, models overfit, and then increasing model complexity will only decrease performance. So hence, classical machine learning mantra is simply simpler models are usually better. But deep learning has overturned this wisdom, because very large models like GPT-3 and others seem to improve linearly with more training data. And new conventional wisdom among deep learning practitioners is that larger models and more data are always better. So I have this nice chart I took from OpenAI blog, so I'll email you the link and chart. I'm sure you've seen it, but for the viewers or maybe readers of the podcast, it would be very instructional. So, we used to think that we need to aim for simpler models, but now the conventional wisdom is, bigger models are much better, perhaps because they capture essentially all of the different exceptions and all the cases. So that was a big surprise.
We'd be happy to post a link to the chart along with the podcast. What are the biggest issues standing in the way of making AI work in practice? Is it data dependency issues that's the bottleneck, or is it a question of business education to the opportunities and the art of what's possible?
I see several main problems for making AI more widely deployed. On the technical side, it is getting more data. Deep learning has shown amazing success with speech and image recognition and text understanding, but those were domains with billions or sometimes trillions of examples available. So one technical problem is getting more data and more labeled data. So hence we see now many companies offering data labeling services, but also more attention to self-supervised learning, especially from the Meta, Facebook team led by Jan LeCun. In many other cases, we don't have billions of examples and need learning to work from just one or few examples. And here there is a very active subfield of zero-shot or few-shot learning, and they typically approach it using pre-trained neural networks and transfer learning. And for more complex problems like those involve mathematics, physical, logical reasoning, we need some form of integration of symbolic reasoning with neural networks, as Gary Marcus is a big proponent of this approach.
Yeah. To get AI to work right, and you've argued, of course, there's a big dependence of ML and data science on ML and data science. How did you personally manage to get the right data at the right quality and the right granularity available to the algorithm in your past and ongoing efforts?
So that's a very good question, but I don't have any magic wisdom device here. So when we were working on business projects, my team would try to get all the data that was available at the time. When I was working within telco, banking, or healthcare environment, there's only so much data available. And in addition, there are various restrictions on what data you're allowed to use, depending on whether you're inside the organization or an outside consultant. So usually we'll just use all the data we could get. And if we were building a predictive model, for example, predicting churn, we could evaluate if it's enough by estimating the accuracy of predictive model and estimating what's the ROI of deploying it. Granularity, as you mentioned, the level of abstraction is very important. For example, when I was consulting Tiffany in helping them kind of detect fake jewelry that was being sold on eBay, it's hard to determine looking at individual item if it was fake. But if you looked at the seller and all their connections and all the items that were selling, then it became much, much easier. There were many red flags that one could find when examining the network.
Indeed, indeed. I mean, the big theme here is data is very powerful, and the more you utilize it, the more likely you are to kind of triangulate on the right answer somehow. Speaking of data, any views on structured versus unstructured data? We continue to live in a world where structured data reigns supreme, at least in the corporations, using SQL and the requirement to have relations, when the majority of any data in any organization is unstructured.
Yes, we have actually run KDnuggets poll on the question, what was the largest data set you have analyzed from 2012 through 2020? And the results were amazingly consistent. So majority of KDnuggets readers who are data scientists, data analysts, other data professionals still work in gigabyte range, like 78% in 2020, 80% in 2018, 83% in 2015 were gigabyte or smaller. So overall median response for what was the largest database you've analyzed was between 11 and 100 gigabytes, which comfortably fits on one laptop for each year since 2012. So what this tells me is, most data professionals probably still work with structured data. The curve for this poll was almost the same. And again, I will include the link in the blog you will post. Okay. But there was one interesting part of that curve. There were like section of that curve that indicated petabyte or call them like big data scientists. There was like very small significant gap with almost no answers in 1 to 100 petabyte range, and then there were those who work with kind of web scale giant data sets of 100 and more petabyte data stores. And our other results support this observation that most companies work with data, and most data analysts work primarily with just structured data in gigabyte range. On the other hand, there is this elite group of, web giants and their data professionals who work with extremely large data sets.
Yeah. That gap, that divide seems to only get bigger with time. very briefly, and I know this is a complicated topic, finding the right talent in AI, data science, and advanced analytics is always a big challenge. Retaining it is an even bigger challenge. Do you have any short advice on, talent, how to get it, how to retain it? What's the best thing a company could do?
Well, of course, salary and stock options are a big incentive. But apart from that, I think, data professionals may not stay at the company where their work is unappreciated, even if they're paid a lot. So, data scientists should not be expected to be unicorn and doing everything. It's important to have a good data science team with proper division of labor. Finally, I may be naive, but I think if a company is having a positive impact on the future, the employees, including data scientists, are more likely to stay there.
That's the importance of the mission is a big deal. In your experience, what is missing in the world of AI and data that would make it more of a mainstream activity that all sorts of companies can begin to benefit from?
So it used to be very difficult to deploy AI systems, and machine learning system required a big team of data scientists and engineers. But now we have AutoML, automated machine learning, and also low-code, no-code ML tools that are changing that. And there are many such tools now, like Data Robot, AutoML from AWS, AutoScaleRn, H2O, AutoKeras, Teapot, and many more. So I think that's a big potential game changer.
The final question here in conclusion, and we're so grateful for the time you've given us. This being the start of a new year, any predictions you'd like to share on what you think will be big in 2022 in our world of KDD, data science, AI?
Well, I'm sure that we'll see even bigger language models with trillions of parameters, GPT-4, new thing from Baidu, Super Megatron Turing. Also, more attention will be paid to energy consumption of those, GPU-hungry deep learning models. AutoML and, low-code AI will continue to advance. And I think we'll have AI more application, including in medical diagnostics. In terms of other trends, we'll see growing importance on MLOps, more attention to data labeling and data-centric approaches. And finally, and I think importantly, I hope we'll see more attention paid to responsible AI. With great power comes great responsibility. And, as AI methods and companies increase in power, I see more push from researchers and legislatures, especially in Europe and California, toward addressing legal and ethical challenges resulting from AI successes. So some have suggested 3 principles for responsible AI: fairness, explainability, and sustainability. So it's no longer acceptable to just develop AI technology and not to worry how it will be used and what is the potential for harmful use or misuse. So in that spirit, I would encourage the AI machine learning data science researchers and practitioners to think not only of technical issues, but also of ethical issues that may result from their technology. I'm not expecting, of course, data professionals to resolve any such issue, but I want to encourage them to consider such issue when they choose what to work on.
Great advice indeed. Responsible AI and ethical issues in AI is a big area of focus at the Institute for Experiential AI at Northeastern. We have a huge amount of effort going into that area because we do think it's important for the future, and the principles you outlined are very important. Gregory Piatetsky-Shapiro, thank you so much for the time. It was great having you here on another episode of Legends of Data and AI. Thank you for being with us.
Well, thank you, Usama. It's an honor to be interviewed by a legend such as you, and I look forward to the podcast being published and meeting you in Boston.
All right, looking forward to it.
Thanks for listening to Legends of Data and AI. We hope you enjoyed our deep dive into the world of data and AI. If you're keen to learn more about making data and AI work in the real world and in any organization, join us next episode and subscribe to the podcast. As always, you can head over to open-insights.com to sign up for our email list, learn more about the work we do, and have access to data resources. See you on the next podcast.